Can you see? Hello? Can you see my slides?
No, ma'am. Yes, ma'am.
Okay, actually, before the last class, we stopped here. I told you to do this one. I have done in the class, and this you need to do as a homework. I told you. How many of you have done? I do not know anyway. And also, the assignment is uploaded. I have given you a message yesterday itself. It is uploaded before, like last week, and I think the deadline is on 21st. Is 21st morning, because before you start the class it should be submitted. It's the you can submit even 20 also, on or before it is actually. 20 is a Sunday. So we will continue with the same module, that is stability analysis of control system. So I have already mentioned what are the stable regions. As you know, the digital systems and the continuous time systems have different regions of stability. In S-plane, that is the continuous time system, you know that the left half of the left half poles are all stable, the same. It is any pole that lie to the right half of S-plane will make the system unstable. Okay. And so the first step is to analyze. Already we have done the Bebo stability analysis. That's what done in the last class. To analyze using root Hurwitz, what you need to do is you will be given a characteristic equation or a transfer function in terms of Z, because it is you need to analyze the digital control system stability. So what you know is the in Z plane, if all the poles, especially the we are concentrating on closed loop poles because we are concentrating on the roots of the characteristic equation. So the roots of the characteristic equation is nothing but the closed loop poles. Okay, it may not be the open loop poles. So that's what the last slide has shown for the homework problem. I have told that the same. So here, what you need to do there is the aim or the idea is you will be given a transfer function in discrete or in z domain. That is, your transfer function, the variable will be z. That means when you solve for the characteristic equation, you will get the closed loop poles which are in terms of z is equal to say minus 0.1, or z is equal to minus 1.2, or z is equal to plus 3, or something like that. Okay, so that is to be converted back to S-plane so that we can apply the Routh-Hurwitz, because Routh-Hurwitz is a continuous domain analysis where you need the regions of stability are same as that of continuous domain. Okay, so that is the idea. So what we have to do is we have to convert back from Z to back to S. That is, we have already have the conformal mapping, that is Z is equal to e to the power st. Okay, so e to the power st, where what is S in terms of Z? That's what you need to find out. So you know that it is ln of Z, you have to take and like e to the power, as it is e to the power st. To eliminate e, you need to take the natural log, that is ln. So when you take ln of e to the power st, you will get st, where s is the s-plane or s is a function in S domain, and t is the sampling period, as you know. And the left hand side is z, so you need to take ln of z also in the left hand side also. Otherwise, you cannot write it as z is equal to e to the power st is equal to z, and z is equal to st. Ln of z is going to be equal to st, and from where you will get as s as 1 over t ln of z. So ln, the natural log is an infinite series. You know that it's a power series expansion. So we cannot do the power series expansion for all the roots to find out the roots. So that is why we are going for a bilinear transformation. So the bilinear transformation is used to convert a transfer function HAS of a linear time invariant system in the continuous time domain to a transfer function HD of Z. It can be vice versa also. That's why of a linear shift invariant, the only condition that is to be satisfied for bilinear transformation is the only condition that is to be satisfied for bilinear transformation is it should be in time domain should be linear time invariant, and in frequency or the in Z domain or in discrete domain it should be linear shift invariant. So that's what it is written. So it maps the positions on the omega axis, that is S is equal to j omega, in the S plane to the unit circle, that is mod Z is equal to 1, that is in the Z plane. So that is done as bilinear transformation. Why the name bilinear? So in bilinear transformation, what we are doing is we are only taking the first order approximation of this infinite series. So that is what here it is written. This already I have mentioned the pole, what are the regions of stability of S. Okay. So here, as you know, as this slides are already uploaded, okay, it is very simple. The bilinear transformation is a first order approximation of the natural logarithm function. There is an exact mapping of the Z plane to the S plane. Okay. So when the Laplace transform is performed on a discrete time signal, the result is precisely the Z transform of the discrete time sequence with the substitution of Z is equal to e to the power st. This is what we have done with the conformal mapping. Actually, we have derived it with the starting from the basic Laplace and Z transform equation. Okay, so that is there already in chapter or module 2. So this bilinear approximation is solved, as I said. So what we are doing is Z is equal to e to the power st. Take ln of Z, will eliminate e to the power st in the right hand side, so that here, here Z is equal to e to the power st means it will be ln of Z is equal to st. And what is S? S is equal to 1 over t, where t is the sampling period. 1 over t into ln of Z. Okay. So this is actually 1 by t ln of Z. It is, I told you, it is a ln of Z is an infinite series. You will say it as an infinite power series. So because you know that ln is a natural log. So it is actually ln of Z itself is Z minus 1 by Z plus 1 plus 1 by 3 Z minus 1 by Z plus 1 the whole cube plus 1 by 5 Z minus 1 by Z plus 1 all powers. 5 plus 1 over 7 Z minus 1 by Z plus 1 the whole to the power 7 all divided into it is already it is this full ln of Z, this full into 2. Okay. So 1 by t. So that into 2 I have taken from the expansion. So 2 by t into this. When you do the first order approximation means only we are taking the first order. That is why only first order? This first order approximation we are doing, but it should be somewhat accurate also, isn't it? We cannot just like that cut all the other values. So anyone can tell what is the idea behind the first order in this case? That is, this is a fraction z minus 1 by z plus 1. So only first order is taken, that is this is to the power 1. Okay. And what happens for z minus 1 by z plus 1 to the whole power 3? Hello? Anyone can tell me why this can be eliminated? If you add that also, you will get very low difference in the decimal points. So what is that value? Z minus 1 by z plus 1. Say, for example, if I am putting z as, say, 2, always here you can see that it is denominator is z plus 1, 1 plus eta, and the numerator is going to be z minus 1. So, of course, if you take this ratio, what happens? This will be, the denominator is always greater than the numerator. And to the power 3. So, if you have a power 3 and a less than 1, that is a fraction less than, value less than 1 to the power 3, becomes again less, isn't it? What is the power of 0.1 to the power 3? What is 0.1 to the power 3 or 0.2 to the power 3? അറിയാവോ ആർക്കെങ്കിലും 0.1 or 0.2 to the power 3? What is the value? Hmm? Anyone? ആരും ഇല്ലേ അവിടെ? Navesri?
Hello, ma'am.
0.1 to the power 3 എത്രയാണോ?
E raised to അങ്ങനെ.
E raised to 0.1. I didn't tell anything E. 0.1.
Okay.
0.1
Zero.
ഒരു വാല്യൂ കേട്ടിട്ടുണ്ടോ? ടു ദ പവർ 3. എത്രയാണ്?
Zero
അറിയില്ലേ?
point zero. 0.001.
0.1 to the power 3 is 0.1 into 0.1 into 0.1, isn't it?
Yes.
എന്താ പറയാ? 0.001 ആണോ?
അല്ല
0.1 into 0.1 എത്രയാണോ?
0.001, ma'am.
ഓക്കെ. എന്ന് പറഞ്ഞാൽ നമ്മളിപ്പോ ഇഫ് ഐ എം considering only one decimal point, what is its value?
Hello, ma'am.
If I am considering only to one decimal place, that means
Zero.
if I have 1.0123, okay,
Yes.
I take only one decimal place means it is 1.0, isn't it? Oh, no.
Yes. Yes. Yes.
Okay, so that is the idea here, because if you have z plus 1 in the denominator and to the power 3 and again to the power 5 എന്തായിരിക്കും? 0.1 to the power 5, it is going to be 0.000, 0.1 into 0.1 into like that 5 times you have to do, isn't it? അല്ല എന്താ പോയിന്റ് കഴിഞ്ഞ് 4 സീറോ കഴിഞ്ഞിട്ട് 1 അല്ലേ വരിക? അതൊക്കെ നെഗ്ലിജിബിൾ വാല്യൂസ് ആണ് ഇവിടെ, അല്ലേ? Is that clear? Hello? What is the approximation that is done in the first order approximation? That is, the other orders, the higher orders are negligible. Hmm? So that is what he had done. So st by 2 here, you are getting s is equal to 2 by t, z minus 1 by z plus 1. So st by 2 into st by 2, if I am cross multiplying here, it is s. So st divided by 2 is z minus 1 by z plus 1. That's what it's put here. And of course, t is for a given digital control, or for a given transfer function, or for a given characteristic equation. T is going to be a constant, the sampling period of that one. Okay, so here st by 2 I can put always, t is of actually maybe it is 10 kilohertz, maybe it is 1 megahertz, whatever it is going to be a numericals. So st by 2 I can put it as another variable w. Okay, so that w will be z minus 1 by z plus 1, or from this expression you will get z as, you cross multiply, you will get w into z plus 1 is equal to z minus 1, and from here you will get z dash 1 plus w by 1 minus w. What is that from here? If you take wz to the side, or this z to here, okay, wz minus z is equal to minus 1 and minus w. So to get it as plus 1, you usually make this minus 1 towards this, so that it will be plus 1. Minus 1 towards the left hand side becomes plus 1. So 1 plus w into 1. So that is why 1 plus w into 1, that is equal to what? Z into this wz is coming here. So z into, that is minus, plus wz is coming as minus wz here, z into 1 minus w. So that is what z is equal to 1 plus w by 1 minus w. Is that clear? Any doubt you are having? Like after doing the bilinear approximation or bilinear transformation, bilinear transformation is nothing but it is a first order approximation. So z is equal to 1 plus w by 1 minus w, where w is a plane which is same as that of, same in the sense you will have st by 2, where is a, that is S plane. Okay, st, if for t is equal to 1 or 2, okay, it is having the same points as that of the S plane. So w resembles the S domain. So that is what the final essence of this. Okay, so the transformations that transforms the circles in the Z plane onto a vertical line, and a complex plane is, say, the W plane is of the, you can say that the unit circle, isn't it? So whenever you have Z as 1. Hmm? Z as 1. Okay. That is transformations on the unit circle. Okay. What will be the value of W? W will be 0, isn't it? So that is W is a real value in the S domain, and it is going to be on the imaginary axis. Okay. So here, uh, this is actually I told you how will you do the Ruth Hurwitz. Okay. The above transformation transforms the interior of the unit circle. Okay, mod is that it is actually less than also on to the left half of the W plane, which is referred to as the bilinear transformation. And once the characteristic equation in Z is transformed to the W domain using this, okay, so the characteristic equation now it will be in terms of W. That Z has gone because we are substituting instead of Z as 1 plus W by 1 minus W, and the Ruth-Hurwitz criterion can be applied to the equation in W in the normal fashion. That is what we are doing in Ruth-Hurwitz. Ruth-Hurwitz, I am not going to teach again because already you have done your and previous or later classes. So the Ruth-Hurwitz criterion, you know already it will determine the number of poles, close to poles in the left half, to the right half, and on the j omega axis. On the j omega axis, now also the j omega axis relate with now it is as it is W plane. Okay, it will be W is equal to j omega. So here there is an example for doing a Routh-Hurwitz stability criterion. Determine the stability of the following digital system. This is just to verify. So because it is only second order, we know that you can directly find as z square is equal to minus, it's equal to 0.25, and z is equal to root of 0.25, which you will end up with 0.5, 0.5 into 0.5, you will get 0.25. So the roots are already known, but this is actually like an illustration, like how it is finding using this transformation and ending up with the correct results. So transforming the characteristic equation z square into W domain using the bilinear transformation, you will get a you have to do this, okay? Like z square means z is you put z is equal to 1 plus W by 1 minus W, the whole square minus 0.2 is equal to 0. So I have done it, and you get Yeah, hello. I had a net interruption in between. Hello. Am
Yes,
I
ma'am.
audible now?
Yes,
Yes,
ma'am.
ma'am.
Okay, okay. So I need to present again. My net has some problem. It is interrupted in between. Hello, can you see? Hmm. Okay. Can you see my slides?
No, ma'am.
Hello. Okay, then now I have connected from the mobile data, so it may be having some problem. I do not know. Okay. We will try anyway. Otherwise, you have seen that the first column of the root array, okay, first column of the root array is showing like all positive, isn't it? There is no sign changes in the first column. So that inferences from the root array that there are no closed to poles that lie to the right half of W plane. W plane is the analogous S plane. Okay. That is, the stability regions are the same as that of S plane. W plane is having the stability regions as same as that of
Ma'am,
the,
ma'am, do you
yeah.
presenting this slide?
Yeah, I told you, no, it is having some delay. Maybe it may come. Okay. So now I'm saying with the previous slide that I have shown to you. Okay. There is already uploaded in UT isn't it? You may be having it, isn't it? These slides are there in your UT the same slides that I am presenting now. Okay. Hmm? If you want, any of
Okay,
you wants, you can take from ET Lab now in your mobile or the laptop. Okay, it's the same.
okay, ma'am. Okay, ma'am.
It is having I'm usually using a Wi-Fi broadband that has gone. Okay, now. So we may stop now. The only thing is you need to do the second problem in that z cube is given. So here, as I have told, this no sign changes in the first column of the root array. Therefore, the system is stable. So here, as I have begun the example, that is z square minus 0.25 is equal to 0. Of course, you can solve it because as it is very like second order only, you will end up with the answer as z is equal to zero point 0.5. So z square is equal to 0.25. The closed loop, as it is the characteristic equation, the roots of the characteristic equation is nothing but the poles of the closed loop poles of the system. So in Z, it is you are obtaining it as Z is equal to Z square is equal to 0.25 means Z is equal to root of 0.25, which is nothing but zero point 0.5, isn't it? So two roots, it will be plus or z is equal to zero point 0.5 square will give you, that is you can write it as plus or minus 0.5. If it is plus or minus 0.5 also, it is coming in the z plane as inside the unit circle, isn't it? That we have already done the z plane when you are doing the conformal mapping, you have seen that what is s plane mapped or s values of the uh, force given to you in S plane is mapped to Z. Then you have already seen that. Okay, so if it is plus zero point 0.5 or minus zero point 0.5, it is coming, the modulus of Z is less than 1, isn't it? No. Eh? Modulus of 1 less than 1 alle. No. Hello? Hello? Am I audible? Hmm? നിങ്ങൾക്ക് മിനി പ്രോജക്റ്റിന്റെ ക്ലാസ് ഉണ്ടോ ഇപ്പോൾ? ഹലോ?
ഇല്ല മാം,
ഏ?
ലിങ്ക് ഒന്നും ഇട്ടിട്ടില്ല.
ഹലോ?
ഹലോ,
ഇല്ല. ഓക്കെ. So please do that z to the power 3, that problem, no? Okay, I think now it may be coming. And now can you see the slides? Hello?
യെസ് മാം.
Nama Rajesh,
Hello?
കാണാമോ slide?
Yes, ma'am. Yes, ma'am.
Yeah, okay. So here, this is the thing that we were explaining, isn't it? Yes, we have done like this, and root array now it's developed without any uh, positive, that is sign changes. That is, all are positive values. Otherwise, if there is a negative value, means we will write as negative because this multiplication, as it is only second order, it is if the coefficients are positive, it is getting positive. But for others, may not be. Like for higher powers, always the analysis for stability comes when the order is like three or more than three usually. So fourth order polynomial and all, it is time consuming for solving for all the rows to force. So in that case only we are going for the stability analysis. I have started with the z square just to give a illustration for the Rutherford analysis as bilinear transformation. So please do this, okay? Do this problem, and also I may upload some practice problems that also you can check maybe by before you come to the Friday's class. Okay. So here, this is already I have done. I think it is there in your app. So jury stability we will start in next class. Before that, I may put some practice problems. So please try to do that. Okay. So that in, some of the practice problems from this, that is from Ruth Harris. Okay. So z to the power 3, and what happens when it is z to the power 4. As you can see that as we move on the powers of in both Harris, so you need to do this bilinear transformation. So that is also a tedious work because you have to find z, you are putting z square to 1 plus w by 1 minus w the whole to the power 3. Okay, so 1 plus w by 1 minus w to the power 3, you need to do 1 plus w the expansion, 1 plus w the whole power 3 expansion, and also 1 minus w the whole power 3. If it is to the power 4, again, So that is also time consuming. That is the drawback or the disadvantage of the bilinear transformation, and we are converting it back to the S-plane and finding the root of this. So jury has come with a stability analysis where it is not needed to convert it to the S-plane. Jury is doing the stability analysis in the Z-plane itself. So how that will be done in the next class will be. Okay, is that okay? For the time being, we will stop now.
Yes,
Okay. Okay. Friday in our hour we will continue. Okay. Before that, please do some examples in Ruth Harvest, because if I do a Ruth Harvest step by step, it will itself carries maybe 45 minutes. Okay. So okay, see you.
okay, ma'am. Thank you.